In this section, we'll talk about the variance of a discrete random variable. So just like we wanted to find the mean or the average of a random variable, we're also interested in the variance of the random variable. So this would be the variance of that entire population of values you'd get if you did the experiment millions or billions of times. So the variance is a much harder formula to do. We'll only do this one once or twice by hand because it is a lot harder to do. The variance, you'll take each x value and minus the mean, square it, and times it by its probability, and you'll do that for each one and add them up. We'll also use our symbol, sigma squared for x, and we'll just put a little x there to remind ourselves that it's for a random variable and not for a data set. The standard deviation of x is the square root of the variance, so we just get rid of the square and use the symbol sigma, and again we put a little x there to remind ourselves that it's for the random variable x. So let's try it. From past experience, Linda knows the probability distribution for her car sales per week. So here's our car sold and the probability for each one. Let's find the standard deviation of the number of cars that she sells. So we can write down each of our possible x values and each of the probabilities. And then I like to do it in a table just so I don't lose track of what I'm doing. So we'll take each x value, so 0, minus the mean. Now I didn't tell you the mean, so let's go ahead and figure that out. So the mean x, or if you prefer, expected value, if you remember, is the sum of each x value times each probability. So let's try that. So we'll have 0 times 0.3 plus 1 times 0.4 plus 2 times 0.2 plus 3 times 0.1, which is 1.1. So that's our expected value, or our mean. So we have 1 minus 1.1 squared times its probability of 0.3. And then here we have 1, it's our next x value, minus the mean of 1.1 squared times its probability of 0.4. Notice this is very similar to our standard deviation that we did for an actual list of data values. We just have to add times by the probability to weight it, because zeros are more likely than 3, so we weight it with the probability. Okay, then we'll have 2 minus 1.1 squared times 0.2, and 3 is my last x value, minus the mean of 1.1 squared and times by its probability of 0.1. Now, let's find the total by adding all of them. So I wrote down here what each one would be, and I added them up to get 0.89. So that means my variance of x, or if you want, we can do sigma squared of x, is equal to 0.89. Now my standard deviation then, and for some reason we don't write SD of x, it's just not a tradition, but my standard deviation of x would just be the square root of the variance. So square root of 0.89 gives me 0.9434. So that's the standard deviation for the number of cars that she will sell per week. And we interpret this just like we do the standard deviation for a data set of numbers. Okay, it's just some way to describe the range of our x values. Now, you can try for this one for the number of trucks she sells, and then we can compare our results. So we had our results for Linda's car and truck sales. Okay, and we want to know which one has a higher expected value, which one has a higher standard deviation. So for cars, we had a mean of 1.1 and a standard deviation. Let's put x's on to remind ourselves this for random variables, and a standard deviation of 0.9434. For trucks, you should have found this when you did it yourself. We had a mean of 0.7 and a standard deviation of 0.6403. Let's see, and then I graphed the two probability distributions for you. So you can see when we look at it for cars versus trucks, that cars has a bit more spread. Our values go from 0 up to 3, whereas trucks go from 0 to 2. My expected value is a lot higher for the cars. She's likely to sell more cars. But the standard deviation is also higher, which means my values are more spread out. So if we were to compare the averages again and think about what this means, so my mean is 1.1 and the trucks, my mean is 0.7. So on average, she sells more cars. So on average, she'll sell more cars. But what do the standard deviations tell us? The standard deviation is higher for cars and lower for trucks. So lower standard deviation means you're more consistent or there's less variabilities. So this means she might sell more cars on average, but there's less variability on the number of trucks, or like she could do a better job of predicting the number of trucks she'll sell for the week because it doesn't change as much from week to week. There's less variability, it changes less from week to week.